Good morning, students. In the previous class, we were discussing about atomic sizes. Generally, we have seen that left to right atomic size decreases. Is it right? First, we will concentrate that point here. After completion of clarity of that point, we will come across with Lanthanide contraction also. Now, let us see. In D block elements, if you take one series, that is nothing but period only, left to right, what will be happen to atomic size? In the form of graphs, they have given. Now, observe this graph, all of you. On x-axis, they have mentioned the elements. If you see this green line, is representing 3D transition series. That means scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay. Now, coming to this blue dotted line, it is representing next 4D transition series. Next red line, it is representing 5D transition series. On y-axis, we have radius in nanometers. Observe this graph carefully, all of you. It is very important. Like this, radius is increasing. 12, 13, 14, 15, 16, 17, 18, 19. If you observe this green line, it is below. That means this green line elements have lower atomic size. That is transition series 3D. See, first 3D series, next 4D series, next 5D. Top to bottom. These elements all are in one range like this. Lowest. That means here. Next to 4D. Top to bottom, what happened to atomic size? Increases. That is known thing for us. Is it right? So according to that, between 3D, coming to 3D to 4D, what happened to atomic size? Increases only. That's why that curve of 4D will be like this. 4D to 5D also increases only, but that increase is very small. If you observe this curve, difference between green line and blue line is greater, but coming from blue line to red line, almost they are getting coincided, but slightly red line is greater than blue line, meaning 4D series is smaller than 5D, but that increase of 4D to 5D is very small. Here we will get the property of Lanthanide contraction. Why? That increase in atomic size from 4D to 5D is very small. That is explained by Lanthanide contraction later. First, before that one, we will observe the series atomic sizes, what will be happened. Are you getting my point, ma? Now, let us see. Scandium. Concentrate on 3D series now. 3D series left to right. Scandium to zinc. 3D series left to right. Scandium to zinc. See, scandium almost 16. Next, titanium 14. Vanadium less than 14. Chromium 13. Manganese slightly less, iron slightly less, cobalt. Okay, if you see, observe this one, from scandium to cobalt atomic size is decreased. But from cobalt to nickel, again it is increased. Nickel to copper, again it is increased. Copper to zinc, again it is increased. Is it correct? So up to nickel, up to cobalt, it is decreased only. According to our known thing, left to right, atomic size decreases. So by following that property, up to nickel, up to cobalt, up to cobalt it is decreased only. But cobalt to nickel slightly increased, nickel to copper increased, copper to zinc also it is increased. This reason we will see. Same it is observed in next series also. Decreased up to rhodium. Next rhodium onwards slightly increase only. Same it is repeated for next series also. So why this is happening? In a period also, why it is happening? Now we will concentrate. After that we will move on to Lanthanide contraction. By that this atomic size explanation will be completed, ma. Okay, let us see first. In scandium 3d1 4s2. Actually, coming to shielding effect order, S is greater than P, P is greater than D, D is greater than F. S is greater than P, P is greater than D, D is greater than F. This is the shielding effect order. S subshells have higher shielding effect than P, P subshells. P subshells have higher shielding effect than D, D subshells have higher shielding effect than F. That is correct. Now we are not comparing S and P or P and D also. We are comparing with D electrons. D1, D2, D3, like that we are going to compare. Is it okay, ma? Now, what is the explanation? Let us see. First, scandium. Scandium contains 21 protons. Third shell 3d1, fourth shell 4s2. Titanium contains 22 protons. Third shell 3d2, fourth shell 4s2. Vanadium contains 23 protons. Third shell 3d3, 4s2. Coming to this scandium to cobalt. Scandium to cobalt. Next element 3d4. 24 protons, 3d4, 4s2. Next 25 protons, 3d5, 4s2. Like that we are seeing from left to right. Scandium, titanium, vanadium, chromium, manganese. Okay, ma? Let us see. Now, when the electrons are entering into 3D, now we are concentrating on 3d1, 3d2, 3d3, 3d4, 3d5. Shielding effect of this one. That means same d orbital, same d subshell we are going to discuss. Into the same d subshell, when electrons are increasing, shielding effect increases. I am not comparing with any SRP. Once again I am telling, I am comparing with only D subshell. See, 3D1, 3D2, 3D3. Like that only I am comparing. So when the number of electrons are increased into the 3D subshell, what happened to shielding effect increases. Now I am writing the point. When the electrons in 3D subshell increase, comma, shielding effect shielding effect increases. I hope you are understanding. When the electrons in 3D subshell increase, shielding effect increases. So scandium to zinc, keep on, shielding effect is going to be increased. But one small explanation is, scandium contains 21 protons. Scandium contains 21 protons. Titanium contains 22. Nuclear charge is increased. Okay, shielding effect is slightly increased. 3D1 to 3D2, shielding effect is slightly increased, slightly only. Nuclear charge increases from 21 to 22. So here, scandium to titanium, titanium to vanadium, vanadium to chromium, chromium to manganese, like that. Scandium to cobalt, scandium to cobalt, nuclear charge dominates shielding effect. Scandium to cobalt, nuclear charge dominates shielding effect. That means when compared to shielding effect, nuclear charge increases more. Because of that, this nuclear charge will hold the outermost electrons strongly. When it holds the outermost electrons strongly, that means from scandium to titanium. From scandium to titanium, increasing shielding effect is dominated by increase in nuclear charge. Slowly I am telling you, observe carefully. From scandium to titanium, increase in shielding effect is dominated. Actually, shielding effect is increased, nuclear charge is also increased. Okay, increase in shielding effect is dominated by increase in nuclear charge. Then this nucleus will hold the outermost electrons very strongly. When it is going to attract the outermost electrons strongly, this outermost electrons slightly they will come closer. When they come closer, what will be happened? Size of the atom decreases. Okay, that only happened. Scandium to titanium, size of the atom is decreased. Okay, because increase in nuclear charge, see, increase in nuclear charge dominates increase in shielding effect. Increase in nuclear charge dominates increase in nuclear charge. Shielding effect, sorry. Okay, ma? Now, because of increase in nuclear charge dominates the increase in shielding effect, shielding effect is not that much applied here. So this nucleus will hold the outermost electrons very tightly. Because of that, slightly they will come closer. Size decreases. Next, from titanium to vanadium also, what will be happened? Increase in nuclear charge dominates increase in shielding effect. Then this one also will hold the outermost electrons. See, number of outermost electrons same only. Will hold the outermost electrons tightly only. Because of that, from titanium to vanadium also, what will be happen to size? Decreases. Next, vanadium to chromium also, increase in nuclear charge dominates increase in shielding effect. That also leads to the nucleus will hold the outermost electrons very strongly. Because of that, from vanadium to chromium also decrease in size we will see. Scandium to titanium, titanium to vanadium, vanadium to chromium. Up to here, slightly atomic size decreases only. But from chromium to manganese, the decrease is small. Manganese to iron, iron to cobalt. These three elements, manganese, iron, cobalt. See, chromium to manganese, manganese to iron, iron to cobalt. These three things, what is going to be? Increase in nuclear charge, increase in nuclear charge is almost same as increase in shielding effect. Increase in nuclear charge is almost same as increase in shielding effect. I will write in the conclusion final point. See, from scandium to chromium, increase in nuclear charge dominates increase in shielding effect. Because of the decrease in atomic size is high. Now, from chromium to cobalt, increase in nuclear charge is almost same as increase in shielding effect. Then here shielding effect is getting increased as well as increase in nuclear charge also getting increased. Both are in same ratio almost. When both are in same ratio, nucleus cannot hold the outermost electrons very effectively because of shielding effect is considerably increased. Previously that much increase is not there. Less number of electrons now slightly getting electrons increased also. Here nuclear charge increased and screening effect increased. Both are getting balanced. Means same ratio. As they are in same ratio, this one is not able to hold this 4s electrons not that much very effectively. Because of that, what will be happened? There is a slight decrease only in the size. Are you okay? That's why manganese to iron, iron to cobalt, chromium to manganese decrease only, manganese to iron, iron to cobalt. Almost they are similar. Almost they are similar. Next, from cobalt to nickel, nickel to copper, copper to zinc, what is going to happen? Last three elements. Increase in nuclear charge is dominated by increase in nuclear charge is dominated by increase in shielding effect. Increase in nuclear charge is dominated by increase in shielding effect. Because of that, what will be happened when shielding effect is increased? When this is acting like a very good shield, this nucleus cannot hold the outermost electrons easily. This is because attraction between nucleus and outermost electrons are disturbed by these electrons. That is only shielding effect. When that shielding effect dominates nuclear charge, this nucleus cannot hold the outermost electrons. So outermost electrons are a little bit away from the nucleus, then size of the atom increases. That's why from cobalt to nickel, nickel to copper, copper to zinc. What happened to size of the atom? Increases. See, cobalt to nickel, slight increase. Here, shielding effect is slightly dominating the nuclear charge. Here, shielding effect furthermore increases. Shielding effect dominates higher than nuclear charge. Here, furthermore shielding effect dominates. That means when we move from scandium to zinc, initially shielding effect is low, nuclear charge is high. Okay, now when we come to the middle, both are getting balanced, nuclear charge and screening effect. Now when we move further, shielding effect is more and nuclear charge is less. Like that, according to the atoms left to right when we are moving, here shielding effect and nuclear charge are playing important role to explain the atomic size variation. Now final conclusion of these points I will write now. I think you understood the points now. If anything doubt is there, you can reach me, no problem. I will clarify once again. But before that, easily you can remember. See, scandium to chromium. What happened? Nuclear charge dominates screening effect. When nuclear charge dominates screening effect, nuclear charge is more than screening effect, then nucleus will hold the outermost electrons more effectively, then size of the atom decreases. So scandium to chromium, atomic size decreases. Next, chromium to cobalt, nuclear charge and screening effect are almost same. When both are almost same, screening effect is there and nuclear charge is also going to be balanced. Because of that, almost they contain same sizes. So atomic size decreases slightly, very slight decrease. Previously from 10 to 7, 7 to 4 like that, but now it is 5 to 4, 4 to 3 like that, very slight decrease will be happened. Now cobalt to zinc, nuclear charge was dominated by screening effect or shielding effect. Both are same only, ma. Screening effect or shielding effect, both are same only. Nuclear charge was dominated by screening effect. Then what will be happened? Atomic size increases. That's why from cobalt to zinc, what will be happen? Atomic size increases. These are the important points you have to note down in the classwork, okay, for understanding these curves. But these are at the time of revision, why this is happening, you can understand. But main important point is here, lanthanide contraction. Is it okay, ma? Now let us see once again. Scandium to chromium in the same series. What happened in nuclear charge and screening effect? These are the two important properties which are playing important role to understand the atomic size variation. Okay, nuclear charge dominates screening effect. When nuclear charge dominates screening effect, there is a decrease in size will be happen. Next, chromium to cobalt, nuclear charge and screening effect are almost same. Atomic size decreases slightly. Cobalt to zinc, nuclear charge was dominated by screening effect. Atomic size increases. These are the points you have to remember why this type of variation is happening in D block elements. Generally we will discuss that left to right atomic size decreases only, but here up to chromium the decrease is applied very highly. Chromium to cobalt almost similar only. See the points. Next, cobalt to zinc, again it is increased. Like that, two properties, depending on two properties, we will explain this curve easily. Those two properties are nuclear charge and screening effect. I hope you understood till now. Now we will concentrate on what about lanthanide contraction. Very important, ma. You have to understand and you have to apply very keenly. Now let us see that what about lanthanide contraction. Okay, I hope you understood till now whatever it is explained. Now let us see once again this graph only. This green line is representing 3D transition series, blue line 4D, red line 5D. From 3D to 4D, increase in atomic size is high. See the gap. Increase in atomic size is high, but 4D to 5D, almost they are coinciding also. Observe this blue line and red line, almost they are coinciding. Is it okay? That is because now the explanation is see scandium, yttrium, lanthanum. Scandium, yttrium, lanthanum. Titanium, zirconium, hafnium. Vanadium, niobium. Okay, these are not that much here. Left side two groups are there. S block. S block. Now we started with the D block. Let us see scandium. This is 3D series. This is 4D series. Okay, from 3D to 4D, according to our expectation only, there will be increase in size, because normally from top to bottom what will be size, what will be happen to size, atomic size increases, because even though nuclear charge is increased, as electrons are entering into new shells, when electrons are entering into new shells, automatically size of the atom also increases. That is everything known to us. From top to bottom, what happened? Atomic size increases. So 3D to 4D, if you think this is 3D graph and this is the 4D graph, some considerable increase in atomic size will be happened. But coming to 4D to 5D, that increase is not that much applied, because here one group of elements are present, that group is called lanthanides. That is only F block. Okay, for your information, I am telling that F block elements, lanthanides, belong to third B group and sixth period. Already 1, 2, 3. 3 are completed, 3 periods. Fourth period only D block elements will be started. Fifth, sixth, 1, 2, 3, 4, 5, sixth. Sixth period. Location of lanthanides, sixth period. They belong to third B here. One more time. Lanthanides are not rows, that means periods. Even though they are separately represented under the table, under the periodic table, 14 elements are there, lanthanides. We have written horizontally. That 14 elements we have written horizontally, but they are belonging to same group only. They are not belonging to period mark. Are you getting my point? They are all belonging to same group only. All the 14 elements belong to same group. For example, if you think this as the periodic table, first period, second, third, now fourth onwards only, D block elements will be started. Fourth, fifth, sixth. This is third B. Okay, this is sixth period. Here, between S block element and That s block element means here lanthanum is there, ma. That only I have shown. See, in between this lanthanum and hafnium 14 elements are there. Those 14 elements are belonging to third B group only. They are not period elements, even though they are written horizontally. Actually, under the periodic table we have written like this. These are lanthanides and these are actinides. Like that we have written. Even though they have written in a horizontal way, they are all belonging to same group only here itself. They are belonging to third B group and sixth period. Is it okay? Now, third B, scandium to yttrium. Scandium to yttrium, no disturbance at all. If you think scandium atomic size is 15 nanometers, for example. Yttrium atomic size is, this is scandium, yttrium atomic size is 17 nanometers. Okay, because top to bottom what will be happened, atomic size increases only. But coming to yttrium to lanthanum, lanthanum atomic size is 18 only. Lanthanum atomic size is 18 only. From scandium to yttrium, that increase is high. But yttrium to lanthanum, that increase is not that much high. Almost both are same only. Because here lanthanides are there. Because of lanthanides, what will be happened? See carefully. In lanthanides, electrons are present in 4f. First lanthanide contains 4f1, for example. Next, 5d, 6s, 5d10, 6s2. Okay, next lanthanide, 4f2, 5d10, 6s2. Lanthanides, what did I say actually? They are belonging to same group. Same group means top to bottom what should be happened? Atomic size increases. Should be happened. But here what is happening here? Atomic nuclear charge is increased. Electrons are entering into 4f. When electrons are entering into 4f, 4f has very poor shielding effect. 4f has very poor shielding effect. Somewhat 5d contains high screening effect when compared to 4f. Even 5d screening effect is also less only. Here, because of very poor shielding effect, this nucleus will hold the 6s electrons strongly. Nucleus will hold the 6s electrons strongly. But coming to here, this nucleus coming to 4f, poor shielding effect. From top to bottom what happened? Nuclear charge nuclear charge increases. Here nuclear charge dominates screening effect. Nuclear charge dominates screening effect. Then this nucleus, here poor shielding effect. Here also poor shielding effect. This nucleus will hold the 6s electrons very much strongly, because first lanthanide to second lanthanide, what happened? Nuclear charge increases. First lanthanide to second lanthanide, what happened? Nuclear charge increases. Then nuclear charge increases. This one will hold the outermost electrons very much strongly when compared to first lanthanide. So when compared to first lanthanide, second lanthanide will hold the outermost electrons very strongly, then size slightly decreases. Not that much, slightly decreases. Instead of increasing, it is happening with decreasing, even though they are belonging to group. Lanthanides belong to group. Next coming to, this is first lanthanide. This is second lanthanide. Coming to third lanthanide. Further nuclear charge dominates screening effect. So this one will hold the 6s electrons furthermore strongly. Because of that, this one will come furthermore closer. Okay. Now lanthanides belong to a group. Lanthanides belong to group. But in lanthanides from top to bottom, atomic size is not increased. Atomic size is getting decreased. Because of poor shielding effect caused by 4f electrons, nuclear charge is increasing, dominating the screening effect. Then this nucleus will hold the outermost electrons very effectively. Because of that, the atomic size is getting decreased. The decrease in atomic size when we move from top to bottom in lanthanides is called lanthanide contraction. The decrease in size in lanthanides from top to bottom is called lanthanide contraction. Why we are concentrating here highly this lanthanide contraction? Generally in a group, top to bottom atomic size increases. But here in lanthanides, from one lanthanide to another lanthanide, what happened to size? Decreases. Contraction is nothing but decreases. That is because of poor shielding effect caused by F shell electrons. That is called lanthanide contraction. Once again, decrease in atomic size of lanthanides because of poor shielding effect caused by F subshell electrons. Because of poor shielding effect caused by F subshell electrons is called lanthanide contraction. Decrease in atomic size of lanthanides because of poor shielding effect caused by F subshell electrons is called lanthanide contraction. Now because of this lanthanide contraction, what will be happened? In between this 4D and 5D series, we have lanthanides. Okay, suppose this yttrium, how much ma? 17. This lanthanum, 18. In between that, 17.1, one lanthanide is there. 17.1 minute ma? 17 point some 9 like that. 17.9, 17.8, 17.7. Just 1 second ma. Yes, correct only. 17.7, 17.6 like that. Up to some extent it will decrease. Again sudden increase. 18 lanthanum. Lanthanum belong to D block actually. Okay. From yttrium to lanthanum, both are D block elements only. Slight increase in atomic size only. But in between them we have 14 elements which are belonging to lanthanides. Okay. Those lanthanides size will be decreased. Because of that, what will be happened? That is called lanthanide contraction. So between 4D and 5D, that much increase is not observed. Between 4D and 5D, the atomic size increase is not that much observed because of presence of 14 elements. Because of presence of 14 elements. Okay. Now let us see what is the explanation, all of you. The property is called lanthanide contraction. See here. The curves in figure 8.3 show an increase from the first to the second series, means 3D to 4D series of the elements, but the radii of the third series, that is 5D series, are virtually the same as those of the corresponding members of the second series. That is almost same only. That much increase is not observed. Okay. This phenomenon is associated with the intervention of the 4f orbitals. In between 4d and 5d, we have lanthanides. That is only 4f orbitals, which must be filled before the 5d series of elements begin. The filling of 4f before 5d results in a regular decrease in atomic radii, called Lanthanide contraction. The filling of 4f before 5d, that is because poor shielding effect is caused by 4f. Then nucleus will hold the outermost electron strongly. Okay, results in a regular decrease in atomic radii called Lanthanide contraction, which essentially compensates for the expected increase in atomic size with increasing atomic number. Okay, the net result of the Lanthanide contraction is that the second and third D series exhibit similar radii. The net result of the Lanthanide contraction is that the second and third D series exhibit similar radii. Example, zirconium 160 picometers, hafnium 159. See, zirconium, hafnium. This is second series, this is third series. Zirconium, hafnium, almost same. Zirconium 160, hafnium 150. See, there is a decrease only from zirconium to hafnium. That is because Lanthanide contraction, and have very similar physical and chemical properties. When the atomic sizes are almost same, they must contain almost similar physical and chemical properties also, much more than expected on the basis of usual family relationship. I hope you are understanding, man. This Lanthanide contraction is very important, and consequences of Lanthanide contraction is also very important. This is the consequence. See, the net result of the Lanthanide contraction is that the second and third D series exhibit similar radii. When they exhibit similar radii, they must contain almost same physical and chemical properties. Okay, and have very similar physical and chemical properties, much more than that expected on the. Generally, same family means same physical properties and chemical properties will expect. More than that, they are showing almost similar physical and chemical properties because of presence of this Lanthanide contraction. Okay, ma? Next, the factor responsible for the Lanthanide contraction is somewhat similar to that observed in an ordinary transition series and is attributed to similar cause, that is the imperfect shielding, that means poor shielding effect of one electron by another electron in the same set of orbitals. However, the shielding of one 4f electron by another is less than that of shielding effect of 4f electrons is less than that of d electron by another, and as the nuclear charge increases, it is dominating the shielding effect. Along the series, there is fairly regular decrease in the size of the entire 4fn orbitals. Okay, ma? The decrease in metallic radius coupled with increase in atomic mass results in a general increase in the density of these elements. Thus, from titanium to copper, the significant increase in the density may be noted. When the size decreases, volume also decreases. When the volume decreases, density will be increased. So there is a significant increase in density from scandium to copper will be observed. That is the explanation of this atomic size. I hope you are clear about this explanation, everyone. Okay, see how much time it took to explain this atomic size. Here they gave one tabular column. In this, all the things they mentioned: scandium to zinc, electronic configuration, enthalpy of atomization, ionization enthalpy. Next we are going to discuss in next class. Metallic ionic radii. This thing, standard electrode potentials, no need. Just this is for reference purpose only. Up to here you can refer. Metallic and ionic radii. Ionization enthalpies we are going to discuss in next class. So in today's class, we have completed explanation of atomic sizes variation. Okay, see, variation in atomic and ionic sizes of transition metals. How atomic size is varied, in the same way ionic sizes also will be varied. Same thing. main thing here, lanthanide contraction, we have to concentrate. So in today's class, we have concentrated on fully variation of atomic sizes only. Okay. And why this much gap is between 3D and 4D, and between 4D and 5D, that gap is very less. That is because of lanthanide contraction. Everything it is explained clearly, and remember and write the notes very neatly. Okay ma? In the next class we will start with ionization enthalpies and variation of ionization enthalpies in D block elements. Okay? I hope you are very clear. If any small sort of doubt also, you can ask me through WhatsApp or through call. I will clarify your doubts. Thank you all. Have a nice day.